go ahead and get going. Okay, so we left off last time. We were talking about some storage saccharides, storage polysaccharides specifically, and we were talking about glycogen. We had just talked about various forms of starch, right? Or the ones that you usually find in plants, okay? And so glycogen is going to be your storage polysaccharide. This is typically going to be found in animals. This is how you actually would store your sugars, okay? Now notice this is distinct and different than your fat, okay? So for example, you'll notice that we have fat that tends to conglomerate, usually down here, right? And then we have it down here around our bellies, thighs, and then our booty, okay? We also get a bit in our cheeks, don't we? Okay, and so those are all fat, right? But if you look real closely at somebody that's really reduced their fat content to the absolute max, you'll notice there's some spots that actually are very stubborn. They don't feel flabby. They feel kind of hard, right? Or another way of looking at it is, have people actually seen somebody with a big beer belly? Anybody ever actually like poked it? No? Okay, so it's like hard, right? Anybody that's poked it or felt a beer belly? It's not flabby, is it? It's hard, okay? And the reason for that is that's actually glycogen storage. So glycogen storage typically happens around your muscles, so areas around your muscle, and around your liver mostly. That's your big glycogen storage, okay? And glycogen storage is used to modulate your sugar content, all right? So you're going to use that whenever you have low sugar, low blood sugar. You start getting tired. What should happen is your body should start releasing glycogen, okay? And when you have too much sugar, you just ate something sugary, it should go ahead and store that glycogen. Now, this is actually a pathway that is not, let's say when it functions correctly, it functions well. In humans, though, it oftentimes has issues, okay? And there's been a lot of research being done lately, and it has been tied to a number of health issues, really massive number of health issues. And a lot of the current health crisis that's going on in the U.S. is directly tied into blood sugar levels and the amount of sugar you're getting, and thus partially related to glycogen, okay? Okay, so anyways, again, this is typically around your livers, your biggest storage, but also around your muscles because this is the primary energy source of these things, okay? It is the only energy source for your brain and is the only energy source directly for your heart usually as well, okay? So without this energy source, you would die very short order. So glycogen is going to be identical in structure to the amylopectin. So if you remember your amylopectin, that was that branched one, right? See the branched one? Okay. The only difference here is, if you remember your amylopectin, that was every 25 glucose units, right? So when we look at glycogen, this is going to be every 12 glucose units. Oh, I'm overriding the other professor on the other end. Okay. So it's much more branched, about twice as branched as something like an amylopectin, right? And this makes it a bit more dense in terms of energy storage, okay? So glycogen is going to be hydrolyzed to glucose in your liver. It's going to be sent in the bloodstream. This is going to help you maintain a fairly constant glucose level in your blood when you haven't ingested sugars, okay? So when your blood glucose level goes low, this is going to start getting digested and releasing sugar into your blood. Okay. Ideally, you should actually have essentially a even blood glucose levels throughout every day, all the time, with just slight peaks and lowering depending on brain and heart activities. Okay. You shouldn't actually have wild swings. Unfortunately, you actually do have wild swings quite often, actually. And so it is not exactly a perfect process. There is some lag to it, and there are some issues that can develop fairly easily in it. Okay? So the large amount of branching in the molecule actually allows for quick hydrolysis when the glucose is needed because you have more ends that you can work on, right? So how you hydrolyze these starch, amylopectin, glucose, all of these, is you actually chop away at the end. Okay? And so you digest it from the end. If it's all one long chain, you can only digest that one chain at a time, right? The more chains you have coming off of it, the faster you can digest it. Okay? Why would we need something more branched than a plant? Do plants really care how big they are? Not really, right? Do plants really care if they can like immediately react to something? If something starts eating them, are they gonna run away? No. And so we need to be able to access those energy storages immediately, don't we? So that we can boost our blood glucose level, get our brains and hearts working real well, and run the heck away from that thing trying to eat us. Okay? And so that's the why we have more branching, right? As animals. So structural polysaccharides, this can be cellulose. Cellulose is going to contain beta-1,4 bonded glucose units. This change in glycosidic bond configuration is going to alter the overall structure of your cellulose compared to that amylose. And so you won't see the same sort of winding structure as you would of amylose. The amylose coils into your alpha glucose chain. The beta bonded chain of the cellulose is actually going to be straight, and that's because these are actually used as fibers. They're like little rods that your cells for a plant are going to use for structural support. Okay? You actually kind of already knew this, that plants are made up of fibers, because everybody's probably messed around with stalks and split them into little ropes, right? Little fibers. A lot of people have braided them, maybe. Anybody done braiding with them? No? No? Has anybody ever seen cotton? That's cellulose, right? It's just real fine fibers. Okay? Has anybody ever taken like wood and got split up in little splinters? That's the fibers, right? You're splitting it down along the fiber. Okay? Instead of across. All right, so many of these straight chains of cellulose are going to line next to each other. This is going to form strong, rigid structures, very strong in one direction in terms of mechanical force, less strong in the other in terms of mechanical force. So if you push down on it, it's actually very strong in terms of mechanical force. In terms of splitting, it's actually much weaker if you push down. That's why you split a tree like this, right? Okay. So, we as humans cannot digest cellulose. You can't digest plant stalks, right? Or bark or any of these things. And so it's actually still, though, an important part of our diet because what it does is it helps clean out our systems for stuff that we digested, but maybe not everything, and it would have left some waste in there. Okay? You got to remember that, has anybody seen what the intestines look like? No? Nobody? Okay, so what they look like is they're not smooth-walled. They have little protrusions. And this helps the food get in there so it can more easily be absorbed. Gives you more surface area, right? But it also means that anything that does not get used and absorbed tends to just sit in there, right? And it's actually quite difficult to push it along if it's just little small granules, right? And so if you get larger objects, let's say cellulose, right, because you couldn't digest a whole structure, then you're going to end up pushing that and it'll wipe them clean, right? Okay? And that's actually the purpose of fiber in your diet, isn't it? Okay? All right, very good. So let's talk a bit more about structural polysaccharides. Here we have chitin. This is going to be a polysaccharide. It's makes up the exoskeletons of insects and crustaceans. It's also the cell walls of most fungi. And this is actually part of why people have allergies to fungi oftentimes, is chitin structures. So it's modified beta-D-glucose. This is actually called N-acetyl glucosamine. It has a beta 1,4 glycosidic bonds. Notice that it's not actually just pure glucose like the previous ones were, partially because it's not a pure structural molecule, right? It's very much a pure digestive molecule. It's a structural molecule, right? And so an amide group is actually going to replace your hydroxyl group. That would be on carbon 2. So like the cellulose, the chitin is actually going to be structurally strong material, has many uses. You can use it for surgical thread, for example, that will actually biodegrade over time. And so as your wound heals, your surgical thread actually degrades and comes off on its own. Okay? And then you don't have to go in and get somebody to remove the surgical thread, like back in the day you used to. Okay? All right, so chitin is actually present in insects' exoskeletons. It serves to protect them from water. Chitin can actually be used for waterproof paper as well. So you can actually make waterproof paper with chitin. You can make like plastic wrap that's actually a paper wrap with chitin, and that's biodegradable. Okay, and so you can actually do quite a few things with it. When you grind it, the chitin powder actually holds moisture in it. And so oftentimes you'll see this being applied to like cosmetics and lotions. It's actually a very safe alternative that's much better for the skin. Okay? And so it's kind of an interesting thing. This has been a kind of a old thing that's come back. Yeah. And it's actually very good. Okay, I don't know how well you guys can actually see this, but this one right here is chitin. So right here, let's see if I can expand that out actually. My resolution is just so low. Okay, that's a little better, right? All right, so this right here is amylose. That's the unbranched form of starch right there. You're probably most familiar with it in terms of things like potatoes, right? That being probably the most starchy food that you would see. And that's why the inside potatoes are typically a like pure white color, right? This is amylopectin right here. That's the branched starch. And so about every 25 glucose units, we got a branching. And that's what that looks like. This right here is cellulose. And so it's a straight chain. Notice the very distinctively different bonding here. See how that? Right there. Okay. So we got a beta 1,4 linkage right here. And that gives a very straight chain structure. Okay. Would this be particularly great for having some sort of structural integrity? No. It'd be like trying to make a house out of springs, right? Not gonna work out very well for you? Not really, right? Yeah, it'd be bouncing around everywhere. And so this right here is chitin actually, and there's the amide right there that we were talking about. Right there as well. Okay. Okay, so let's talk about carbohydrates in blood. So red blood cells are going to have a number of chemical markers. These are going to be bonded to cell surfaces. They're going to include the ABO blood markers. They'll contain 3 to 4 monosaccharides. These right here being the important monosaccharides that are going to be involved in this process. So here we have D-galactose, L-fructose, fucose. I never got a water before I came here. Hey, it was like somebody was asking me questions the entire time since I came. Okay, so then this next one is going to be N-acetylglucosamine. And this one's going to be N-acetylgalactosamine. And so these are going to be the 4 components that will determine whether you have ABO blood types, right? These are the markers on your red blood cells that tell your body, hey, I'm a friend, I'm part of you, okay? And without those, if you have a different marker on your blood cell, it would tell your body, hey, I'm not a friend, kill me, right? And so your immune system would then try to attack it and start targeting. Okay, and so this is actually type O blood. And what you see is you have N-acetyl glucosamine, then galactose, and then fucose. And so that is type O right there. And so your blood, your immune system will attach, read that code, and go, hey, okay, type O. We're good. All right, what do you notice about all the other ones? Type B and type A versus type O.
They have the same chain, but the type A and type B branch off with something different.
Exactly. Yeah. So you actually have type A and type B that only have a single modification from that, right? They have one additional group. So type O is actually the same as the others. And so does anybody know what the universal donor is? Yeah, type O, right? And that's because when the immune system attaches, that's designed for these, attaches to this one, doesn't have anything that shouldn't have. Okay? And so, interestingly enough, it could have developed in such a way that it would actually have still attacked this because it doesn't have that thing, but it did not. So it binds onto this and goes, you're okay. Okay? Mm-hmm.
I know there's a negative and a positive,
Mhm.
but it didn't refer to anything. What's the difference with like an O negative and O positive?
So that's rho factor. Actually, let me finish this chapter, and then we can go into rho factor, okay? Okay, sorry. Okay. Yeah, we could do like a little module or something if you want. I just want to make absolutely certain I actually finish today. Okay, so each person's immune system, of course, is going to recognize only its normal carbohydrate set, ABO. It's going to destroy what it considers foreign blood types that are not ABO and attack those. It's going to see those as enemies. So because of the trisaccharide on your O type, of course, this is going to be present on all blood types, and so none of the no blood type actually recognizes the O carbohydrate set as foreign, and that ends up being a universal donor, of course, so that you can give to anybody. The AB type blood, by the way, is actually considered the universal acceptor, and that's because their immune system actually binds to both and says, yes, those are it. Okay? So they actually have both types in their blood. All right. And so an AB blood type can actually take all the blood types ABO, not including rho factor. Yeah, that was a good point. So any blood transfusion can be accepted by an AB blood type. Okay? An O type is universally screwed over. They can give to everybody, but they can't take anything from anybody but O, right? And so if I remember correctly, it's O negative. It has an extremely hard time getting blood. If I remember correctly, my younger brother is actually that. And he's in the Army, so it's kind of, he's like, God, I better not get shot. Anyways, so this right here is a little summary chart of what I just said. This right here is going to be your carbohydrates in your blood. So we have heparin here. This is going to be a polysaccharide. This actually prevents clotting. Heparin is going to be highly ionic polysaccharide. It's going to have many disaccharide units that link together. This is the disaccharide unit that composes heparin. This is right here. See these negative charges here? That's why it's referred to as highly ionic. Okay. These are called glucosaminoglycans. They're going to have these highly charged repeating disaccharide units. Notice there's a 4- charge on that for every disaccharide unit. Again, this is mainly due to these sulfate groups right here. That's 3/4 the charge on it, right? Yeah. And so those are the main cause of its highly charged. Okay. Okay, so this is the overall study guide for this chapter. And this would be what you should take out of each section. Okay? And everybody probably recognizes that as being something I put on every end of chapter. Remember the PowerPoints are online, right? Okay. Okay. All right, so Let me go ahead and I'll